In the vast, unyielding expanse of our solar system, where the sun's light fades to a mere whisper across billions of kilometers, there lies a realm of perpetual twilight, a frozen frontier that stretches beyond the orbit of Neptune, the outermost of the gas giants, into a domain where temperatures plunge to the brink of absolute zero, preserving ancient secrets in layers of ice that have remained untouched since the dawn of planetary formation some 4.5 billion years ago, a time when the swirling disk of gas and dust around our young star coalesced into worlds, leaving behind these silent sentinels as remnants of that primordial chaos, drifting in slow, elliptical paths that speak of gravitational tugs and ancient migrations, their surfaces etched with the subtle scars of cosmic radiation and occasional collisions, yet holding within their cores the potential clues to the very building blocks of planets, including perhaps the origins of water and organic compounds that seeded life on Earth. As we contemplate these frozen worlds, one cannot help but feel a quiet sense of awe, a meditative reflection on the isolation and endurance of these distant bodies, each one a microcosm of the solar system's history, suspended in the cold vacuum, waiting for the faint probes of human curiosity to unveil their mysteries. Beyond Neptune's azure haze, at distances ranging from 30 to 50 astronomical units from the Sun, where 1 AU marks the average span between Earth and our star, the Kuiper Belt unfolds like a vast, toroidal cloud of icy debris, home to millions of trans-Neptunian objects, or TNOs. These enigmatic wanderers, composed primarily of water ice intermixed with frozen methane, ammonia, and carbon monoxide, their rocky interiors shrouded in volatile ices that sublimate ever so slightly under the feeble solar warmth, creating tenuous atmospheres on the larger ones, while the smaller fragments remain as pristine planetesimals, untouched by the geological processes that reshape the inner planets. And in this frigid environment, where temperatures hover around minus 230 degrees Celsius, the ices form crystalline structures that trap gases and dust from the solar nebula, offering scientists a frozen archive of the conditions prevailing during the accretion phase, when giant planets like Jupiter and Saturn flung these bodies outward in a grand dynamical reshuffling, scattering some into highly eccentric orbits that carry them far beyond the classical belt, into the scattered disk, where objects like Eris dwell in elongated paths that bring them perilously close to Neptune's influence at perihelion, before retreating to the outer darkness, their surfaces reddened by the relentless bombardment of cosmic rays that polymerize hydrocarbons into complex tholins, those reddish-brown organic macromolecules that give many TNOs their distinctive hues, evoking thoughts of distant, alien landscapes painted in shades of rust and charcoal against the stark white of exposed ices. And as we delve deeper into this narrative, consider the discovery of these worlds, beginning with Pluto in 1930 by Clyde Tombaugh at the Lowell Observatory, a speck of light that shifted against the stellar backdrop, initially hailed as the ninth planet, but later reclassified as a dwarf planet, and the archetype of the Plutinos, a subclass of TNOs, locked in a 3-to-2 orbital resonance with Neptune, meaning for every 3 circuits Neptune completes around the Sun, these objects complete 2, a gravitational dance that stabilizes their paths against close encounters, preventing ejection or collision. And since that pivotal find, telescopes have revealed a burgeoning population, with the first confirmed Kuiper Belt object beyond Pluto, 1992 QB1, now known as Albion, spotted by David Jewett and Jane Liu, using the University of Hawaii's 2.2-meter telescope on Mauna Kea, marking the onset of a new era in solar system exploration, as surveys like the Deep Ecliptic Survey and the Outer Solar System Origins Survey have cataloged thousands more, estimating that hundreds of thousands of bodies, larger than 100 kilometers in diameter, populate this region, their collective mass amounting to perhaps a tenth of Earth's, far less than initially theorized, suggesting that the belt was depleted by dynamical processes or that planetesimal formation was inefficient in these distant reaches, where the solar nebula thinned and accretion slowed, leaving behind a sparse assembly of icy conglomerates that occasionally fragment into short-period comets, those ethereal visitors that grace our skies with tales of sublimating gas and dust as they venture inward, a reminder of the interconnectedness of the solar system's architecture, from the scorching realms near Mercury to these frozen outposts. Among these frozen worlds, Pluto stands as a beacon of complexity. Its surface, a mosaic of terrains, revealed in exquisite detail by NASA's New Horizons spacecraft during its flyby in 2015, showcasing vast plains of nitrogen ice dubbed Sputnik Planitia, where convection cells churn slowly beneath a hazy atmosphere of nitrogen, methane, and carbon monoxide. The heart-shaped region, contrasting with rugged highlands of water ice mountains towering up to 3 kilometers, their peaks sculpted by glacial flows and sublimation pits, while the dwarf planet's largest moon, Charon, presents a fractured landscape with chasms deeper than the Grand Canyon, hinting at a violent past, perhaps involving cryovolcanism or tidal stresses from its synchronous lock with Pluto, and together they form a binary system where both bodies orbit a common barycenter outside Pluto's surface, a testament to Charon's substantial mass, nearly half that of its companion. And beyond this duo, smaller moons like Nix, Hydra, Kerberos, and Styx tumble in orderly paths, their irregular shapes betraying origins as collisional debris reassembled in the aftermath of a cataclysmic impact that may have birthed the entire system, mirroring the hypothesized giant impact that formed Earth's moon, yet in this case occurring in the cold outer solar system where ices dominate over rock, preserving the evidence in frozen splendor. And as we ponder Pluto's demotion to dwarf planet status in 2006 by the International Astronomical Union, based on its failure to clear its orbital neighborhood of similar objects, we recognize it as the harbinger of a diverse family, including Eris, discovered in 2005 by Mike Brown and his team at Palomar Observatory, a body slightly smaller in diameter but more massive than Pluto due to its higher density, suggesting a rockier composition beneath its methane ice veneer, its orbit in the scattered disk, taking it from 38 to 97 AU, a journey of 557 years, during which its surface freezes solid at aphelion, collapsing any atmosphere into frost, only to sublimate anew as it approaches the Sun. And Eris' moon Dysnomia, a diminutive companion, adds to the intrigue, as spectral analyses reveal similarities to Pluto's surface, with methane and nitrogen ices altered by irradiation, producing ethane and other hydrocarbons, while the dwarf planet's slow rotation, possibly tidally locked, contributes to its enigmatic thermal profile. Observed through occultations and infrared telescopes like Spitzer and Herschel, which estimate its albedo as remarkably high, reflecting nearly all incoming sunlight, a property shared by many large TNOs whose fresh ices act as mirrors in the void. Venturing further into the belt, we encounter Haumea, a rapidly rotating dwarf planet named after the Hawaiian goddess of childbirth, its elongated, football-like shape resulting from a spin period of just under 4 hours, the fastest among large solar system bodies, likely the outcome of a colossal collision that stripped away much of its icy mantle and spawned a family of smaller objects sharing similar orbits and compositions, rich in crystalline water ice, a signature of shock heating from the impact. And Haumea's 2 moons, Hiyaka and Namaka, orbit in planes that hint at this disruptive event, while ground-based spectroscopy detects a dark red spot on its surface, possibly a concentration of irradiated organics or salts, adding layers of complexity to its geology. And not far in dynamical terms lies Makemake, another classical Kuiper Belt dwarf planet, its surface dominated by frozen methane and ethane, with traces of nitrogen, as revealed by the James Webb Space Telescope's near-infrared observations, which pierce the veil of distance, to map volatile distributions, showing seasonal variations as its 309-year orbit brings different hemispheres into view. And Makemake's small moon, informally called MK2, discovered by Hubble in 2016, suggests that satellite formation is common among these isolated worlds, perhaps through accretion from circumplanetary disks or captured during close encounters in the dense early belt, before gravitational stirring by the giant planets rarefied the population. And as we reflect on these individual portraits, a broader picture emerges of a region shaped by Neptune's resonances, where objects cluster in stable niches like the 2-to-1 or 7-to-4 resonances, their orbits sculpted over eons by the planet's migratory history, as simulations indicate that Neptune's outward push during the late heavy bombardment era excited inclinations and eccentricities, populating the hot classical belt with dynamically excited bodies, while the cold classical population, with low inclinations and circular orbits, represents a primordial disk minimally disturbed. Their redder colors and higher binary fractions pointing to formation in situ, far from the sun's heat, where gentle collisions allowed pairs to survive, unlike the more violent inner regions. And this dichotomy fuels ongoing debates about the belt's architecture, with surveys like the Canada-France Ecliptic Plane Survey and the ongoing Legacy Survey of Space and Time at the Vera Sea. Rubin Observatory poised to uncover fainter, more distant objects, potentially revealing the transition to the inner Oort cloud, that hypothetical reservoir of long-period comets even farther out, influenced by galactic tides rather than planetary perturbations, yet connected through the scattered disk, where extreme TNOs like Sedna reside its perihelion at 76 AU and aphelion at nearly 1,000, an orbit so detached that it challenges standard models, suggesting perturbations from a rogue planet or a close stellar flyby in the Sun's birth cluster, a narrative that weaves these frozen worlds into the larger tapestry of stellar evolution and galactic dynamics, inviting us to linger on the quiet tension of unanswered questions as the faint signals from ground-based radars and space telescopes accumulate, building a mosaic of data that slowly illuminates the shadows beyond Neptune. Turning our gaze to the compositional intricacies, spectroscopic studies from facilities like the Very Large Telescope in Chile and the Keck Observatory in Hawaii have classified TNOs into taxonomic groups based on their visible and near-infrared reflectance, with the neutral gray class resembling dead comets, their surfaces depleted of volatiles through sublimation cycles, while the red class boasts fresh tholins, polymers formed when ultraviolet light and cosmic rays break down methane and nitrogen, recombining into complex chains that absorb blue light, imparting a ruddy glow, and intermediate classes hint at resurfacing events, perhaps cryovolcanic outflows, or impact gardening that exposes subsurface layers, as seen on Kwa'wa, a large classical KBO with evidence of ammonia, hydrate, and crystalline water ice, indicators of recent geological activity despite its small size and remote location, where internal heat from radioactive decay or accretional remnants could drive such processes, melting pockets of volatiles and erupting them onto the surface, freezing instantly in the vacuum. And this potential for subsurface oceans, insulated by thick ice shells, raises intriguing possibilities for astrobiology, though the extreme cold and lack of liquid water make habitability unlikely, yet the presence of organics and prebiotic chemistry preserved in these ices could mirror the conditions that delivered such materials to early Earth via cometary impacts, a hypothesis supported by missions like Rosetta, which analyzed Comet 67P, Churyumov-Gerasimenko, finding amino acids in phosphorus, essential for life, and extrapolating to TNOs, which serve as the source population for such comets, underscores their role as time capsules, their frozen matrices locking away the solar system's chemical inventory for billions of years, undisturbed by atmospheric weathering or plate tectonics, allowing us to probe the protosolar nebula's composition, comparing it to interstellar medium abundances measured by probes like Voyager, now venturing into the heliopause, where the solar wind meets the galactic medium, a boundary that these distant objects orbit well within, yet feel the subtle pull of the Milky Way's tide, which over geological timescales can alter inclinations, contributing to the observed spread in orbital parameters. And as numerical integrations model these effects, incorporating n-body simulations that track thousands of particles under the influence of the giant planets, they reveal instabilities that erode the belt's edges, ejecting bodies into interstellar space or inward as comets, a slow depletion that has reduced the primordial mass by orders of magnitude, leaving the sparse distribution we observe today, a testament to the dynamic violence underlying the apparent serenity of these frozen realms. Continuing our slow journey through the twilight realm beyond Neptune, we find ourselves drawn inexorably toward the subtle interplay of light and shadow that defines these frozen worlds. Where the sun appears as little more than a brilliant point among countless stars, its rays so attenuated that they cast no perceptible warmth upon the surfaces they touch, yet still sufficient to drive the delicate seasonal cycles observed on the largest and most volatile-rich members of this distant population, cycles that unfold over centuries rather than months or years. As orbital eccentricities and inclinations modulate the insolation received at different points along each path, causing ices to migrate slowly across hemispheres in a process known as volatile transport, whereby nitrogen, methane, and carbon monoxide sublimate from sunlit regions and recondense in shadowed or polar areas, gradually reshaping surface topography through frost heave, glacial creep, and the formation of transient atmospheres that rise and fall with heliocentric distance, a phenomenon most dramatically illustrated by Pluto itself, where New Horizons captured images of hazes layered high above the surface, composed of tholin particles lofted by subtle convection, and perhaps even faint cryovolcanic venting, particles that scatter sunlight into a diffuse blue glow, reminiscent of Earth's twilight sky, yet infinitely more tenuous, a ghostly veil that speaks of ongoing chemical evolution in the absence of liquid water or significant internal heat. And as we contemplate this interplay, the question arises of how such worlds maintain any semblance of activity in their extreme cold, leading us to consider the role of radiogenic heating from the decay of short-lived isotopes like aluminum 26 inches, the early solar system, which may have melted interiors briefly during formation, allowing differentiation into rocky cores and icy mantles. And though that heat has long since dissipated for most small bodies, the larger ones Pluto, Eris, Haumea, Makemake, retain faint residual warmth, perhaps augmented by tidal dissipation in binary systems or during past close encounters, enough to sustain subsurface liquid layers in some cases, as inferred from geophysical models that balance conductive heat loss against radiogenic production and possible antifreeze effects from ammonia or salts lowering the freezing point. Models that predict possible oceans beneath tens to hundreds of kilometers of ice on Pluto, where convection in a water-ammonia slurry could drive resurfacing through occasional eruptive episodes, depositing fresh ices that brighten albedo and reset radiolytic darkening, a hypothesis supported by the observed youthful appearance of Sputnik Planitia, whose pitted, convecting nitrogen glacier appears geologically young, perhaps only tens of millions of years old, contrasting sharply with the ancient, heavily cratered water ice highlands surrounding it, and extending this line of inquiry to other large TNOs. We note that Eris, with its higher density suggesting greater rock fraction, may harbor an even thicker ice shell overlying a potential subsurface ocean, though direct evidence remains elusive, confined to indirect constraints from thermal modeling, occultation light curves that reveal atmospheric collapse at large distances, and spectroscopic detections of pure methane ice, which would sublimate rapidly without replenishment, implying either recent activity or efficient cold trapping mechanisms that preserve volatiles in shadowed craters and equatorial bands. While Haumea's rapid spin and elongated shape complicate such interpretations, as centrifugal forces stretch its equator outward, potentially fracturing the icy crust and allowing subsurface fluids to reach the surface in the distant past, though current observations show no active venting, only the lingering signatures of collision-induced melting that crystallized water ice into its present form, distinct from the amorphous ice expected in cold accretion environments. And Makemake, more distant still, exhibits a methane-dominated spectrum with ethane and perhaps tholins, its high albedo suggesting a relatively pristine surface, with minimal darkening, yet ground-based monitoring has detected seasonal changes in brightness and color, hinting at the slow redistribution of frosts as its eccentric orbit carries it from perihelion near 45 AU to aphelion beyond 55, distances where solar flux varies by nearly 30%, sufficient to drive measurable volatile migration over decades of observation. And these seasonal rhythms, though imperceptibly slow to human timescales, underscore the dynamic nature of even the most remote icy bodies, challenging the notion of a completely static outer solar system. And broadening our perspective, we turn to the smaller, more numerous classical Kuiper Belt objects, those cold classicals with nearly circular, low-inclination orbits that appear to have escaped the violent stirring experienced by the hot classical and resonant populations, their surfaces often displaying the reddest colors in the belt, attributed to accumulation of complex organics over billions of years, without significant volatile loss or resurfacing. And among them, objects like 2002 MS4 and 2007 or 10 Gonggong reveal, through Hubble and ground-based photometry, a range of albedos and phase functions, with some exhibiting opposition surges characteristic of rough, porous regoliths, while others show smoother behavior suggestive of icy mantles. And binary systems are particularly prevalent in this cold population, with nearly 30% of large objects possessing companions far higher than in the scattered disk or Plutino groups, a statistic that supports in situ formation in a dynamically calm disk where gentle gravitational interactions allowed mutual capture or co-accretion, binaries that now serve as exquisite laboratories for mass determination through mutual orbital periods, yielding densities that cluster around 1 to 2 grams per cubic centimeter, consistent with mixtures of rock and ice in roughly solar proportions, though outliers like the dense Eris and the low-density Haumea family members highlight diversity arising from collisional processing or compositional gradients in the primordial disk, gradients perhaps linked to temperature-dependent condensation fronts, where different ices froze out at varying heliocentric distances, creating compositional zoning that mirrors the snow lines observed in protoplanetary disks around other stars, as imaged by ALMA, and connecting these distant remnants to the broader process of planet formation. We recognize that the Kuiper Belt preserves a snapshot of the planetesimal population after giant planet migration, with models such as the Nice model and its variants proposing that the outward scattering of icy planetesimals during Jupiter and Saturn's resonance crossing, followed by Neptune's chaotic march through the disk, sculpted the observed structure, exciting inclinations in the hot classical belt, implanting the resonant populations, and populating the scattered disk with bodies on highly eccentric orbits, some of which, like the detached extreme objects with perihelia beyond 50 AU, require additional mechanisms, perhaps a distant massive perturber, a former companion star, or a flyby by a passing star in the Sun's birth cluster to explain their extreme detachment from the giant planet's influence. Objects such as Sedna, 2012 VP 113, and the more recently discovered 2018 VG 18 Farfarout, whose orbits stretch to hundreds or thousands of AU, spending most of their time in near interstellar darkness, where galactic tides dominate over solar perturbations, slowly torquing inclinations and eccentricities over giga-year timescales. And as these extreme TNOs drift ever farther, They blur the boundary between the solar system proper and the inner Oort cloud, that vast spherical shell of icy bodies perturbed into long-period comet orbits by passing stars and molecular clouds. Yet the transition remains poorly constrained, with current surveys detecting only the innermost members, their faintness demanding the next generation of wide-field telescopes to map the full distribution and test formation scenarios, whether in situ accretion at hundreds of AU, implantation from closer regions, or even capture from other stellar systems during the Sun's dynamical youth in its natal cluster. Possibilities that infuse these frozen worlds with a quiet sense of cosmic connectivity, linking our solitary star to the larger galactic environment through gravitational whispers across light years. As the narrative drifts ever deeper into the shadowed architecture of the trans-Neptunian region, the quiet drama of orbital resonances emerges as one of the most elegant signatures left by the solar system's formative dynamical upheavals, resonances that act as invisible gravitational scaffolding, locking certain classes of objects into periodic configurations with Neptune that have persisted across billions of years, preserving pockets of stability amid the broader scattering and depletion that otherwise characterizes this distant frontier. And foremost among these are the Plutinos, whose 3-to-2 mean motion resonance ensures that for every 3 orbits completed by Neptune, the object completes exactly 2, a commensurability that places their perihelia in such a way that close approaches to the planet are avoided, preventing chaotic perturbations that would otherwise eject them from the system or drive them inward to become Jupiter family comets. And this protective mechanism explains why Pluto and its cohort maintain relatively moderate eccentricities and inclinations compared to the more wildly scattered objects beyond, their orbits tracing slow, precessing ellipses whose arguments of perihelion librate around 90 degrees or 270 degrees in what is known as the Kozai-Lidov mechanism when inclinations are sufficiently high, though for most Plutinos the libration is dominated by the resonant forcing itself, creating a gentle oscillation in eccentricity and inclination that keeps them safely distant from Neptune, even as their paths sweep across vast radial ranges. And spectroscopic surveys of these resonant bodies reveal a diversity of surface compositions, with some displaying prominent methane absorption bands overlaid by nitrogen ice, others showing more subdued volatile signatures, perhaps due to prolonged irradiation or past volatile loss. Yet a recurring theme is the presence of tholin-like reddening agents, suggesting that organic chemistry proceeds apace even in this cold, low-energy environment through the slow accumulation of radiation products. And extending outward, we encounter the Tuotino population in the 2-to-1 resonance, objects whose orbits are synchronized such that they complete 1 circuit for every 2 of Neptune's, placing their aphelia near the 47 to 50 AU region, where the classical belt begins to thin. And these bodies often exhibit higher inclinations and eccentricities than the Plutinos, a consequence of having experienced stronger scattering during Neptune's migration phase, when the planet's outward passage through the primordial disk stirred the planetesimal population, implanting some into stable resonant orbits while ejecting or scattering others. And among the Tuotinos, 2002 UX-25 stands out as a relatively large object whose near-spherical shape and presumed hydrostatic equilibrium imply a size approaching 700 kilometers, with density measurements from occultations in binary companions, suggesting a composition rich in water, ice, and rock, though its surface appears darker and less volatile covered than Pluto's, perhaps reflecting greater collisional processing or a history of volatile escape during closer perihelion passages in the past. And further resonances populate the belt at higher order commensurabilities, such as the 5-to-2, 7-to-3, and even 9-to-4, each carving narrow islands of stability where objects can dwell for the age of the solar system. Their clustered arguments of perihelion and nodes hinting at secular forcing from the giant planets that aligns orbits over giga-year timescales, a phenomenon observed in the classical belt as well, where the so-called kernel, a compact group of low-inclination, low-eccentricity objects near 44 AU, exhibits an unusually tight clustering in semi-major axis, possibly a remnant of an ancient shepherded subdisk, or the survivors of an evaporative instability that cleared surrounding material, and these subtle dynamical imprints serve as fossils of the giant planet's early wanderings, allowing theorists to reconstruct migration histories by comparing observed distributions to N-body simulations that incorporate planetesimal-driven migration, gas disk torques, and stochastic scattering, models that have evolved from the original Nice scenario to more refined versions incorporating the early instability hypothesis, wherein Jupiter and Saturn cross their mutual 1 to 2 resonance rapidly, exciting eccentricities and inclinations across the disk, scattering icy planetesimals outward, while Neptune and Uranus underwent chaotic close encounters that reshaped their orbits before settling into their present near-circular configurations. And in this framework, the Kuiper Belt emerges not as a pristine relic, but as a heavily processed remnant, its structure bearing the scars of planetary adolescence. Yet within that processing, certain populations escaped major alteration, most notably the cold classical Kuiper Belt, whose members cluster around 43 to 45 AU with inclinations below, about 5 degrees and eccentricities near zero, their surfaces displaying the reddest optical colors and highest incidence of binaries in the entire trans-Neptunian population, properties that suggest minimal dynamical excitation and gentle collisional histories, allowing fragile binaries to survive and surfaces to accumulate thick mantles of irradiated organics without frequent volatile refreshing or impact gardening. And recent wide-field surveys have begun to map the size distribution and color gradients within this cold classical component, revealing a break in the cumulative size distribution around 100 kilometers, steeper at smaller sizes, consistent with collisional grinding in a primordial disk that was dynamically cold enough to preserve planetesimals, but still experienced enough gentle encounters to fragment the largest members into observable families, and spectroscopic follow-up on representative cold classicals such as 2013 UQ, 10 and 2004 XR, 190 shows, spectra dominated by methanol ice and complex hydrocarbons, with little evidence for crystalline water ice or ammonia hydrates, contrasting with the resurfaced or volatile-rich signatures seen in some resonant and scattered objects, thereby reinforcing the idea that these bodies formed in place, far from the sun's heat and the giant planet's influence, in a region where temperatures permitted the condensation of more refractory organics and methanol alongside water ice, creating a compositional gradient that traces the thermal structure of the protosolar nebula, a gradient mirrored in the volatile inventories of short-period comets, believed to originate from the scattered disk, versus long-period comets from the Oort cloud, though the precise sourcing remains under debate as dynamical models continue to refine the pathways by which objects migrate from their formation zones to their present locations or are lost entirely to interstellar space. Within the intricate web of dynamical classifications that partition the trans-Neptunian population, the scattered disk stands apart as a region of pronounced orbital eccentricity and inclination, a graveyard of objects that once resided closer to the giant planets, but were gravitationally flung outward during epochs of planetary migration and disk instability, their present paths bearing the unmistakable imprint of repeated close encounters with Neptune that increased their perihelia beyond the classical belt, while preserving substantial eccentricities that carry them to distances where solar perturbations weaken and galactic tides begin to assert subtle influence. And unlike the resonant populations whose orbits remain phase-locked to Neptune in protective configurations, scattered disk objects display no such commensurabilities over long timescales, instead exhibiting chaotic diffusion in semi-major axis and slow secular evolution in inclination and eccentricity, driven by the cumulative effect of distant planetary encounters and the Kozai-Litoff cycles, when inclinations exceed approximately 39 degrees relative to the invariable plane, cycles that periodically pump eccentricity at the expense of inclination or vice versa, potentially driving perihelia low enough for significant volatile sublimation during passages near the Sun, or raising them high enough to freeze atmospheres entirely for gigayears. And this dynamical restlessness manifests in the observed surface properties of scattered disk objects, which often appear brighter and more neutral in color than their cold classical counterparts, suggesting either fresher exposures of water ice through impacts or resurfacing, or alternatively, greater volatile content that has been replenished by inward excursions before retreating to colder aphelia, where ices can condense anew from tenuous exospheres. And among the largest representatives of this class, Eris continues to command particular fascination, its diameter measured through multiple occultation campaigns, and combined with mass estimates from the orbit of dysnomia, yielding a density near 2.5 grams per cubic centimeter, indicative of a substantial rocky core, comprising perhaps 60 to 70% of its volume, beneath a volatile-dominated mantle, a composition that contrasts with the lower densities typical of smaller icy bodies and implies either efficient accretion of rocky material in its formation zone or differentiation facilitated by early heating, and spectroscopic observations across near-infrared wavelengths reveal a spectrum rich in methane ice absorption features, with weaker bands attributable to ethane, ethylene, and possibly nitrogen, the methane appearing in crystalline form at certain longitudes, while amorphous at others, a heterogeneity that may arise from seasonal frost migration patterns modulated by Eris's slow 25-hour rotation and its highly inclined 29-degree orbit relative to the ecliptic, an inclination that subjects it to pronounced Kozai oscillations, with a libration period on the order of tens of millions of years, during which its perihelion distance varies between roughly 38 and 46 AU, while eccentricity oscillates in antiphase, ensuring that even at closest approach, the surface remains frigid enough to retain most volatiles, except during brief perihelion passages when sublimation rates peak, potentially generating temporary atmospheric envelopes detectable through stellar occultations that have occasionally revealed central flashes indicative of refractive hazes or extended gaseous layers, though such detections remain marginal and require confirmation with future high-cadence monitoring. And as we linger on Eris, its moon dysnomia provides additional insight into binary formation mechanisms in the outer solar system, with the satellite's orbit tidally circularized and likely resulting from either impact-induced debris, reaccretion, or co-formation in a circumplanetary disk, its size estimated at roughly 700 kilometers, suggesting it captured a significant fraction of ejected material, and mutual occultation events between Eris and dysnomia have allowed precise astrometric measurements that refine the system mass and test tidal evolution models predicting that the binary orbit will continue to widen slowly through tidal dissipation until eventual desynchronization, though on timescales far exceeding the age of the solar system. And shifting attention to other prominent scattered disk members, we encounter Gong, formerly known as 2007 or 10, a dwarf planet candidate whose size approaches 1,000 kilometers and whose highly eccentric orbit ranges from 33 to 100 AU, placing it among the most extreme perihelion distances for large TNOs, while still permitting perihelion passages close enough for measurable volatile activity. And recent James Webb Space Telescope observations have resolved its spectrum with unprecedented clarity, detecting strong methane ice bands alongside ethane and possibly carbon dioxide, with the presence of crystalline methane suggesting either recent deposition or protection from amorphization by cosmic rays through shielding or resurfacing, and the detection of a reddish continuum slope hints at tholin production, though less pronounced than in some classical objects, perhaps due to periodic volatile refreshing that dilutes the irradiated layer. And Gong Gong's small moon, discovered via Hubble imaging, further enriches the picture by allowing density estimates that place it in the intermediate range between Pluto-like volatile-rich worlds and rockier interiors, reinforcing the notion of compositional diversity even within dynamical subclasses, diversity that may trace back to radial gradients in the protoplanetary disk, where carbon-to-oxygen ratios, ice-to-rock fractions, and the abundances of minor volatiles varied with distance from the young sun, gradients now partially scrambled by migration, but still discernible in statistical trends across large samples of TNOs. And broadening the scope once more, we consider the family of objects sharing orbital elements with Haumea, a collisional family whose members display similar very red colors, surface water ice signatures, and tight clustering in proper orbital elements, properties consistent with fragmentation of a proto-Haumea during a high-velocity impact that ejected icy mantle material while preserving the denser core in the primary body, and dynamical backtracking of family member orbits converges to a common epoch several billion years ago, supporting the collision hypothesis over capture or co-accretion scenarios, and the family's spread in semi-major axis and inclination reflects subsequent secular evolution under planetary perturbations, yet their preservation as a coherent group underscores the relative dynamical quiescence of the classical belt compared to the scattered disk, where such families would disperse more rapidly due to stronger chaotic diffusion. And this contrast highlights the importance of location within the belt in determining long-term orbital stability and surface evolution, with cold classicals experiencing the least processing, resonant populations intermediate stability with periodic forcing, and scattered disk objects subject to the most vigorous dynamical stirring, a stirring that occasionally delivers members inward, as Centaurus objects with perihelia between Jupiter and Neptune, where they undergo further evolution into short-period comets or suffer ejection, and the flux of such centaurs provides a measurable link between the distant reservoir and the observable inner solar system, with estimates from surveys like the Outer Solar System Origins Survey suggesting that the scattered disk supplies the majority of Jupiter family comets through a multi-step process of stepwise scattering, each encounter with a giant planet randomizing orbits until capture into short-period configurations occurs. And spectroscopic studies of centaurs reveal transitional surfaces, some displaying cometary activity through outgassing of carbon monoxide or carbon dioxide ices at large heliocentric distances, others remaining dormant with neutral or slightly reddened spectra that evolve toward more comet-like compositions as they approach the Sun, a progression that mirrors the fate awaiting many scattered disk objects over cosmic timescales. And as these considerations unfold, the quiet realization settles that the frozen worlds beyond Neptune are not isolated curiosities, but integral threads in the continuous fabric of solar system dynamics, their present configurations encoding the history of planetary assembly, migration, and interaction with the circumstellar disk. A history that continues to be written in the faint motions of distant light points against the stellar background, motions that future observatories such as the Vera C, Rubin Observatory's legacy survey of space and time, will track with unprecedented depth and cadence, potentially revealing new extreme objects, refining orbital distributions, and constraining the existence or absence of additional distant perturbers that might explain the clustering of arguments of perihelion observed among some detached TNOs, a clustering that has prompted hypotheses ranging from an undiscovered super-Earth to collective secular effects or observational biases, hypotheses that remain under active investigation as more data accumulate. Each new discovery adding nuance to our understanding of this remote, frozen domain, where time itself seems to move more slowly, preserving ancient architectures in crystalline stillness. Deepening our contemplation of the trans-Neptunian realm, we arrive at the threshold where individual worlds give way to collective patterns, where the sparse distribution of these frozen bodies across immense volumes of space reveals statistical truths about the processes that govern the final stages of solar system assembly, truths encoded in the size-frequency distribution that describes how many objects exist within given diameter ranges, a distribution that, when plotted on logarithmic scales, approximates a power law with a slope that steepens noticeably below approximately 100 kilometers, indicating a transition from accretion-dominated growth among larger planetesimals to collisional fragmentation among smaller ones, a fragmentation regime shaped by the balance between disruptive high-velocity impacts and gentle merging collisions in the dynamically excited environment beyond Neptune. And this break in slope, first clearly delineated through deep imaging surveys that reach fainter limiting magnitudes, suggests that the primordial population underwent substantial collisional evolution over the first few 100 million years, eroding the abundance of mid-sized bodies while preserving a handful of survivors that grew large enough to resist further disruption. Survivors now recognized as the dwarf planets and near-dwarf candidates that anchor the upper end of the size spectrum, and when corrected for observational biases, inherent in magnitude-limited surveys biases that favor brighter, higher albedo objects at the expense of darker or more distant ones, the intrinsic distribution implies a total mass in the Kuiper Belt today of perhaps only a few % of an Earth mass, a stark depletion relative to the several to tens of Earth masses thought necessary in the early disk to form the observed resonant structures and supply the comet reservoirs, depletion that dynamical models attribute primarily to long-term leakage through resonances and scattering rather than inefficient formation, with the majority of primordial mass having been ejected into interstellar space, swallowed by the giant planets, or delivered inward as impactors during the heavy bombardment phases. And this mass loss story finds support in the relatively low binary fraction among hot classical and resonant populations compared to the cold classicals, as violent encounters would preferentially disrupt loosely bound pairs, leaving the calm inner regions as the last refuge for surviving binaries, pairs whose mutual orbits provide precise mass and density determinations that cluster around values consistent with roughly 1-to-1 ice-to-rock ratios, when assuming typical porosities, though notable exceptions such as the high-density Eris and low-density Haumea family fragments illustrate how collisional stripping or compositional zoning can produce outliers, zoning perhaps reflecting the sequential condensation of ices as the nebula cooled, with more volatile species like carbon monoxide and methane freezing farther out than water or ammonia, creating radial gradients that migration partially homogenized but did not erase entirely. Gradients now faintly discernible in the average surface colors and spectral features across dynamical subclasses, where cold classical objects tend toward the reddest optical slopes indicative of accumulated complex organics. Resonant bodies show intermediate colors with more variable volatile signatures, and scattered disk members often appear neutral or slightly blue, possibly due to fresh ice exposures from recent activity or impacts during their dynamical youth. And these color trends, mapped meticulously through large photometric catalogs compiled from telescopes in both hemispheres, offer a window into surface modification processes that operate on timescales ranging from orbital periods to giga-years. Processes including cosmic ray gardening that darkens and reddens exposed ices through polymerization of methane and other hydrocarbons into tholins, micrometeoroid impacts that churn regolith and expose fresh material, and, on the largest bodies, seasonal volatile transport that periodically brightens and resets surfaces by depositing clean frost layers, transport whose efficiency depends sensitively on heliocentric distance, albedo, and spin state, with objects spending more time at greater distances, experiencing slower cycles and greater net volatile retention, while those with lower perihelia undergo more vigorous sublimation and atmospheric collapse cycles, cycles that may also drive weak cometary activity, observable as faint dust, Haumea, or outbursts even at large distances. As documented in a handful of active centaurs and distant TNOs, where carbon monoxide or carbon dioxide ices sublimate under minimal solar heating, providing direct evidence that the boundary between dormant icy body and active comet is porous and temperature dependent, rather than sharply defined by dynamical class. And extending this theme of transitional behavior, we note the population of inner Oort cloud candidates, objects with perihelia in the hundreds of AU that bridge the scattered disk to the classical long-period comet reservoir, bodies whose extreme detachment requires either rare dynamical pathways involving multiple giant planet encounters over extended timescales, or external perturbations from passing stars, or the galactic tide acting on weakly bound planetesimals at the disk's outer edge, and the handful of such objects discovered to date, Sedna, with its 76 AU perihelion, 2012 og 13 at 80 AU, 541 og 32 liliakuhunua at 65 AU, and others identified in ongoing surveys, display a remarkable clustering of arguments of perihelion near 0 degrees and ascending nodes near 0, a clustering whose statistical significance has fueled extensive modeling efforts to determine whether it arises from observational selection effects, favoring certain orbital geometries in discovery surveys, from apsidal alignment induced by an undiscovered distant massive body shepherding these orbits, or from collective secular interactions within a massive disk of unseen planetesimals, models that continue to evolve as additional detections fill in the orbital parameter space and test the predicted distributions under each scenario, with the absence of a clear perihelion cutoff or inclination pileup providing important constraints that favor certain classes of perturber over others, and regardless of the ultimate resolution to this orbital alignment puzzle. The very existence of these detached objects underscores the long reach of solar system dynamics, where even at distances where the Sun appears merely as the brightest star, gravitational influences from within the planetary system and from the wider galaxy conspire to shape paths across eons, paths that occasionally bring these frozen relics close enough for detailed characterization through occultations, photometry, and spectroscopy, techniques that have already revealed atmospheric properties on the largest members, such as Pluto's nitrogen-dominated envelope with trace hydrocarbons and hazes, Eris's probable transient frosts, and Makemake's tenuous methane atmosphere detected via occultation, central flashes, and light curve modeling, atmospheres whose escape rates and compositions provide clues to volatile inventories and thermal histories, inventories that may include primordial noble gases trapped in clathrates or ices since formation, gases whose isotopic ratios could distinguish between solar nebula inheritance and interstellar medium contributions now being probed by precise measurements on comets, returned by sample missions, or analyzed in situ, linking these distant frozen worlds to the chemical feedstock that nourished terrestrial planets through late-stage bombardment. And as this interconnected picture slowly coalesces, one senses the profound patience embedded in the outer solar system, where geological clocks tick on scales of millions to billions of years, where surfaces record impacts separated by epochs rather than eras, and where the faint light from a distant star sustains only the subtlest of changes that nonetheless carry the weight of cosmic history, inviting continued observation and reflection as humanity's instruments grow ever more sensitive, piercing farther into the twilight to illuminate what has remained hidden in crystalline quiet for so long. Turning our gaze toward the observational frontiers that continue to unveil the subtle details of these distant frozen worlds, we find that stellar occultations have emerged as one of the most precise and revealing techniques for probing atmospheres, shapes, sizes, and even ring systems around trans-Neptunian objects, a method that relies on the fortuitous alignment of a background star with the object as seen from Earth, causing the starlight to dim gradually as the object's limb crosses the line of sight. The duration and depth of the occultation chord, providing direct measurements of diameter, independent of albedo assumptions that plague reflected light photometry, while multi-chord observations from widely separated stations on Earth yield silhouettes that constrain triaxial shapes, surface roughness through limb irregularities, and the presence of tenuous atmospheres through central flash phenomena, where refracted starlight briefly brightens the geometric center of the shadow, a signature detected unambiguously on Pluto during multiple occultations that mapped the evolution of its nitrogen atmosphere from perihelion maximum pressure in the late 20th century to near collapse at greater distances, and similar though fainter flashes have been reported for Makemake and Eris, suggesting extended gaseous envelopes of methane or nitrogen that refract light over scales of hundreds of kilometers, envelopes whose scale, heights, and opacities imply surface pressures on the order of microbars, tenuous enough to be transient and highly temperature sensitive, collapsing into surface frosts when the object recedes beyond roughly 50 AU, where equilibrium temperatures drop below the triple point of the dominant volatiles. And these occultation campaigns, coordinated through global networks of amateur and professional observatories, have also revealed unexpected complexities, such as possible ring systems around small centaurs like Chariklo and Chiron, narrow rings composed of micrometer-sized particles, perhaps shepherded by unseen small satellites, or arising from debris following disruptive impacts or tidal stresses during close planetary encounters. Rings whose particle orbits remain stable due to the extremely low Hill sphere filling factors at such large heliocentric distances. And while no confirmed rings have yet been detected around classical TNOs, the precedent set by these closer objects raises the intriguing possibility that faint debris structures could exist around the larger dwarf planets, structures that would be exceedingly difficult to image directly, given the overwhelming contrast between the central body and any surrounding material, yet potentially detectable through repeated occultation monitoring that searches for secondary events or anomalous light curve features, and complementing occultations, space-based infrared photometry from missions such as Spitzer, WISE, and now the James Webb Space Telescope has provided thermal emission measurements that constrain effective temperatures, albedos, and beaming parameters that describe how efficiently absorbed sunlight is re-radiated and how anisotropically the emission occurs due to surface roughness and thermal inertia, with low thermal inertia values typical of loosely bound regoliths or porous ices that insulate subsurface layers, allowing diurnal temperature contrast to persist even at slow rotation rates. And for Pluto, the New Horizons infrared spectrometer mapped dramatic regional variations in surface temperature tied to volatile distribution, with nitrogen-rich plains remaining colder due to sublimation cooling, while water ice mountains appear warmer, a thermal dichotomy that reflects the interplay between geology and atmospheric physics. And extending such analyses to more distant TNOs, JWST's mid-infrared instrument has begun to resolve spectral features in thermal emission bands, detecting signatures of crystalline water ice, ammonia hydrates, and complex organics that complement near-infrared reflectance data that together paint a picture of surface heterogeneity driven by both endogenous processes like cryovolcanism and exogenous ones like irradiation and micrometeoroid gardening that on small scales refreshes surfaces by overturning regolith, but on larger scales contributes to the gradual darkening and reddening observed in many objects over gigayear timescales during which the cumulative fluence of galactic cosmic rays and solar energetic particles polymerizes surface hydrocarbons into increasingly complex and refractory tholins. Tholins, whose optical properties dominate the visible and near-infrared appearance of many TNOs, producing the characteristic red slopes that steepen toward longer wavelengths until volatile ices begin to absorb strongly, and laboratory simulations under ultra-high vacuum and low-temperature conditions have successfully reproduced these spectral slopes by irradiating methane, nitrogen, and carbon monoxide ices with energetic electrons or ultraviolet photons, yielding synthetic tholins whose reflectance matches observed TNO spectra remarkably well. And when these laboratory analogs are combined with radiative transfer modeling of layered surfaces, they suggest that most TNOs possess a thin, irradiated crust overlying fresher ices that may be exposed by impacts, glacial flow, or sublimation-driven resurfacing. Resurfacing whose frequency and efficacy vary widely depending on object, size, orbit, and composition, with larger bodies more likely to retain internal heat sources capable of driving episodic activity, while smaller ones rely primarily on external drivers. And this layered model also explains the occasional detection of crystalline water ice on objects too cold for spontaneous crystallization during formation, as amorphous ice formed in the cold outer nebula would require heating above approximately 130 Kelvin to convert to the crystalline phase. Heating that could occur through impacts, close encounters, or brief radiogenic warming early on, and the persistence of crystalline signatures on some small TNOs thus implies either recent exposure of interior material or protection against amorphization by overlying volatile mantles that shield the water ice from direct radiation, a protective mechanism supported by the correlation between volatile abundance and the presence of crystalline features in spectral surveys that continue to expand with instruments capable of higher resolution and sensitivity, allowing finer discrimination between different ice phases, grain sizes, and mixing states that encode the thermal and dynamical history of each body, history that in aggregate reveals the migration and scattering episodes that sculpted the outer solar system, episodes whose timing and vigor are further constrained by the cratering records on Pluto and Charon, imaged by New Horizons, records showing far fewer small craters than expected from collisional models assuming a steady-state size distribution, a paucity interpreted as evidence for either recent resurfacing that erased older craters, or a collisional environment that was depleted in small impactors after the dynamical instability that may have occurred relatively late in solar system history, perhaps as recently as 4 billion years ago during the proposed late heavy bombardment, though the outer solar system's crater chronology remains tentative due to the low impact flux at large distances and the complicating effects of volatile mantling that can bury or modify craters over time. And as these diverse lines of evidence converge, from dynamical simulations to spectroscopic deconvolutions to thermal modeling and occultation inversions, a coherent yet still incomplete portrait emerges of a region rich in preserved history, where each frozen world serves as a quiet witness to the grand processes that assembled our planetary system. Processes whose echoes persist in the slow orbital drifts, the seasonal frost migrations, the gradual chemical maturation of surfaces, and the faint thermal glows that betray internal warmth or recent activity that, though subtle, reminds us that even in the deepest cold of the solar system, change continues on scales attuned to cosmic rather than human rhythms, inviting patient observation as new missions and telescopes extend our reach farther into the twilight, promising to illuminate additional chapters in this enduring narrative of distant, icy solitude. In the meditative expanse, where observation meets interpretation, the ongoing exploration of these frozen worlds beyond Neptune reveals itself not merely as a catalog of distant points of light, but as a prolonged dialogue between human ingenuity and the indifferent quiet of cosmic distances, a dialogue sustained by successive generations of instruments whose increasing sensitivity and spectral resolution peel back successive veils from surfaces that have slumbered for eons. And among the most transformative of these recent advancements stands the James Webb Space Telescope, whose near-infrared and mid-infrared capabilities have begun to furnish unprecedented detail on the volatile and organic chemistry of trans-Neptunian objects too faint and too cold for earlier observatories to characterize fully, revealing, for instance, the presence of ethane and possibly acetylene on Makemake, alongside the dominant methane, compounds whose formation pathways involve either photolytic processing of methane under cosmic ray exposure or low-temperature chemistry in irradiated ices. Pathways that laboratory experiments replicate by subjecting frozen methane-nitrogen mixtures to ultraviolet or particle bombardment, yielding a suite of hydrocarbons whose relative abundances serve as diagnostic fingerprints of the irradiation history and resurfacing frequency on each body. And on Gong Gong, the telescope has detected a surprisingly strong signature of carbon dioxide ice, a volatile less abundant on closer TNOs like Pluto, where nitrogen dominates, suggesting that Gong Gong's greater average distance and correspondingly lower temperatures have favored the retention of this less volatile species while allowing methane to remain prominent. And these compositional distinctions, subtle yet profound, hint at the original zoning of the protoplanetary disk, where carbon dioxide condensed at intermediate distances before more volatile methane and carbon monoxide froze farther out, zoning partially preserved despite the dynamical stirring that redistributed planetesimals. And as JWST continues its cycle observations targeting additional large TNOs, including Quasar, Sedna, and several classical objects, the emerging dataset promises to refine models of volatile stability zones, models that predict which ices should remain stable on surfaces as functions of heliocentric distance, obliquity, albedo, and spin period. Predictions tested against the observed presence or absence of spectral features, with discrepancies pointing either to non-equilibrium processes, such as impact gardening that excavates subsurface ices, or to hitherto unrecognized internal heat sources that locally elevate temperatures above equilibrium values, sources potentially including long-lived radiogenic elements like uranium and thorium, whose decay continues to provide modest but persistent warmth in large rocky cores, warmth sufficient perhaps to maintain subsurface brines, or trigger occasional cryovolcanic episodes on bodies like Quasar, where ground-based spectroscopy has long indicated the presence of ammonia, hydrate, and crystalline water ice, signatures interpreted as evidence for past heating events that melted and recrystallized portions of the icy mantle before refreezing. And though direct detection of current activity remains beyond reach, the combination of spectral youth indicators and geophysical modeling supports the possibility that such worlds harbor transient or episodic geological processes, even in their present frigid state, processes whose traces manifest as localized compositional anomalies or brightness variations detectable only through prolonged monitoring campaigns that ground-based telescopes equipped with adaptive optics and large collecting areas are increasingly capable of undertaking. Telescopes such as the Very Large Telescope, Keck, and the forthcoming Extremely Large Telescope, whose 39-meter aperture will enable diffraction-limited imaging and spectroscopy of fainter TNOs, potentially resolving surface features on objects as small as 200 kilometers at distances beyond 40 AU, and detecting weak atmospheric emission lines or reflectance changes associated with seasonal volatile migration whose modeling has advanced significantly through thermophysical codes that simulate heat conduction, sublimation, and recondensation across rotating, irregularly shaped bodies illuminated by a point source sun, codes that incorporate realistic surface roughness, porosity, and layered compositions to predict temperature distributions, volatile inventories, and observable photometric variations that for Pluto have been successfully matched to New Horizons data and occultation light curves. lending confidence to similar applications for more distant dwarf planets where direct imaging remains limited, but light curves from stellar occultations and ground-based photometry provide the primary constraints, and these modeling efforts further underscore the role of obliquity in modulating insolation patterns. With high obliquity objects experiencing extreme seasonal contrasts that drive polar to equatorial volatile transport that may concentrate frosts at poles or in permanently shadowed craters while depleting equatorial regions, patterns potentially observable as latitudinal gradients in color or spectral absorption strength if future resolved imaging becomes feasible. And broadening the narrative once again, we reflect on how these individual studies coalesce into a larger understanding of the outer solar system's role as a reservoir for primitive material whose delivery to the inner planets via cometary and asteroidal impacts contributed organic precursors, water, and perhaps even phosphorus and other bioessential elements during Earth's late veneer, a contribution whose magnitude and timing remain subjects of active debate, informed by isotopic analyses of cometary ices returned by Rosetta and anticipated from future sample return missions targeting short-period comets of presumed Kuiper Belt origin, missions that would allow direct comparison between distant TNO compositions inferred remotely and the detailed inventories measurable in returned samples, thereby calibrating spectroscopic interpretations and refining models of volatile transport and fractionation in the early solar nebula whose chemical fingerprints persist most faithfully in these cold, minimally processed bodies, whose surfaces have escaped the intense heating and aqueous alteration that affected inner solar system objects. And as this chain of inference lengthens, linking spectroscopic data to dynamical histories to cosmochemical models, a quiet reverence settles over the contemplation of these frozen outposts that stand as silent archives of conditions prevailing when the planets first took shape. Archives whose pages, though written in ice and faint light, continue to yield insights with each advance in observational capability, insights that remind us of the profound continuity between our own world and the most remote corners of the solar system. Corners where time stretches thin and change unfolds with glacial deliberation, yet where the same physical laws that govern familiar landscapes operate with equal inexorability. Inexorability that manifests in the slow sublimation of methane frost under distant sunlight, the gradual polymerization of organics under relentless particle flux, the imperceptible precession of orbits under secular perturbations, and the patient accumulation of knowledge through persistent human effort that transforms the abstract notion of distant icy bodies into tangible worlds of intricate detail and lingering mystery that invites continued exploration, not with urgency, but with the calm persistence suited to a realm where epochs pass between significant events and where each new datum, however small, adds another measured breath to the long, slow respiration of cosmic discovery. As the accumulated observations and refined models draw us further into the contemplative essence of these remote icy domains, a persistent undercurrent of uncertainty regarding the outermost architecture of the solar system begins to surface with greater clarity, an uncertainty centered on the possible existence of additional large bodies whose gravitational influence might subtly orchestrate the observed clustering of orbital elements among the most extreme trans-Neptunian objects, bodies that, if present, would reside at hundreds to perhaps 1,000 astronomical units from the Sun, far beyond the reach of current direct imaging, yet potentially betraying their presence through long-term secular perturbations on the detached population, perturbations that manifest most strikingly in the observed alignment of arguments of perihelion near 0 degrees for objects with perihelia exceeding approximately 60 AU and semi-major axes beyond about 250 AU, an alignment accompanied by a corresponding clustering of ascending nodes and a preference for retrograde inclinations in some subsets, patterns whose low probability of arising by chance has prompted intensive scrutiny of both observational biases and dynamical mechanisms that could produce such coherence without invoking an additional massive perturber. Biases that include the seasonal visibility of certain orbital geometries from Earth-bound telescopes, favoring objects whose perihelia occur during northern hemisphere, winter months, or whose orbits project favorably onto the ecliptic plane during discovery epochs. Biases that sophisticated debiasing procedures applied to survey fields have partially mitigated, yet not entirely eliminated. And while some analyses conclude that selection effects alone might suffice to explain the apparent clustering when full survey characterization is incorporated, others maintain that residual signals persist even after correction. Signals strong enough to warrant continued modeling of hypothetical distant planets, whose masses, orbits, and formation pathways remain subjects of active theoretical exploration that encompasses scenarios in which such a planet formed in situ at large, semi-major axis, through slow pebble or planetesimal accretion in an extended disk, was scattered outward during an early dynamical instability involving close encounters with one or more of the known giant planets, or was captured from another stellar system during the Sun's residence in its birth cluster, where stellar densities permitted frequent close passages and mutual gravitational captures whose probability increases if the incoming body already possessed a substantial eccentric orbit, or if dissipative effects such as gas drag or three-body interactions with passing stars facilitated energy loss, and in each case the perturber's influence on the scattered disk and inner Oort cloud would depend sensitively on its mass and orbital separation, with masses in the range of 5 to 10 Earth masses and semi-major axes between 400 and 800 AU, emerging as favored parameter spaces in many simulations that best reproduce the observed orbital clustering, while avoiding excessive disruption of closer populations, or the telema, generation of unobserved inclined objects, simulations that track the evolution of thousands of test particles under the combined gravitational fields of the known planets and the hypothetical body, integrating forward over gigayear timescales to assess stability, apsidal confinement duration, and the gradual diffusion or erosion of aligned configurations as secular resonances and chaotic diffusion act over longer periods during which the perturber itself would experience subtle orbital evolution due to galactic tides and encounters with passing stars, evolution that might circularize or migrate its orbit slightly, while preserving its ability to shepherd distant planetesimals. And although no direct detection has yet been achieved, despite deep imaging campaigns with Subaru, CFHT, and now the early data releases from the Vera C. Rubin Observatory's precursor surveys, the absence of a counterpart in reflected light does not preclude existence given the extreme faintness imposed by distance and presumed low albedos potentially as low as a few percent if the surface consists of heavily irradiated organics without significant volatile frosts that would brighten appearance but remain unstable at such large heliocentric distances where equilibrium temperatures fall below 20 Kelvin, temperatures at which even nitrogen and carbon monoxide would freeze solidly and remain inert against sublimation. And this thermal regime further implies that any hypothetical distant planet would possess a surface dominated by amorphous water ice, mixed with complex tholins, and perhaps trapped interstellar grains, a composition that would render it among the reddest and darkest objects in the solar system, objects whose detection would rely primarily on thermal emission in the far infrared or sub-millimeter regimes accessible in principle to future facilities, such as the Origin Space Telescope or large ground-based sub-millimeter arrays, but currently beyond practical reach for bodies of modest size at such distances. distances that also place stringent limits on atmospheric retention, with escape velocities insufficient to hold even hydrogen or helium against Jean's escape over solar system lifetimes, leaving only a possible tenuous exosphere of sublimated trace volatiles or sputtered atoms, none of which would produce detectable signatures with present technology. And yet the dynamical imprint, should it prove robust against further discoveries and refined statistics, would represent one of the most significant revelations in solar system science since the identification of the Kuiper Belt itself, a revelation that would extend the known boundaries of planetary influence outward by orders of magnitude and reshape our understanding of late-stage planet formation, disk dispersal, and the interaction between our system and its galactic environment, an environment where stellar flybys, molecular cloud passages, and the overall galactic tide continuously perturb the outer halo of comets and planetesimals, perturbations that over the age of the Sun have populated the classical Oort cloud, with objects on nearly parabolic orbits while stripping others into interstellar space, objects that occasionally return as long-period comets whose compositions rich in carbon monoxide, molecular nitrogen, and exotic ices provide additional chemical context for the distant disk from which they originate, context that complements the more processed volatiles observed in short-period comets from the scattered disk and allows reconstruction of radiochemical gradients across the full extent of the primordial nebula, gradients whose preservation in these frozen archives underscores the extraordinary isolation and stability of the outer solar system compared to the geologically active inner regions, regions reshaped repeatedly by impacts, volcanism, tectonics, and atmospheric escape, while beyond Neptune, the dominant agents of change remain slow, external, and low energy, agents that etch surfaces over billions of years, yet leave the fundamental architecture intact, architecture that future comprehensive surveys, combined with next-generation space telescopes, and perhaps dedicated flyby missions to Pluto-class worlds or even more distant targets, will continue to illuminate layer by layer, each advance revealing not only new facts, but also new questions that deepen the sense of wonder at the quiet, enduring complexity of this twilight frontier, a frontier where the solar system fades gradually into the interstellar background, yet retains its coherent structure through gravitational memory, memory that links the present configurations of distant icy bodies to events that transpired when the Sun was young and the disk still swirled with gas and dust, events whose faint echoes persist in every measured orbit, every spectral absorption feature, every subtle variation in brightness, inviting us to listen patiently to the slow, measured story these frozen worlds continue to tell across the vast silence. Amid the accumulating layers of knowledge drawn from spectroscopy, dynamics, and thermal modeling, a contemplative pause naturally arises when considering the ultimate fate of these frozen worlds beyond Neptune, a fate governed not by dramatic cataclysms, but by the inexorable workings of time across cosmological timescales on which the Sun itself will evolve from its present main sequence stability into a red giant phase, some 5 to 7 billion years hence, a transformation during which the star's outer envelope will swell to encompass the orbits of the inner planets and perhaps reach as far as the asteroid belt, while the increased luminosity will drive profound changes even in the distant Kuiper Belt and scattered disk, changes that will elevate equilibrium temperatures sufficiently to sublimate the most volatile ices en masse, causing nitrogen, methane, and carbon monoxide mantles to vaporize and escape into space at accelerated rates, transforming currently dormant surfaces into transiently active cometary landscapes before the volatiles are entirely lost, leaving behind darker, rockier cores mantled only in more refractory water, ice, and organic residues that will themselves undergo further photolytic and radiolytic processing under the intensified ultraviolet flux from the expanding star, processing that may ultimately carbonize surfaces into tar-like layers resistant to further alteration, And as the Sun sheds its outer layers in subsequent planetary nebula and white dwarf phases, the diminished gravitational binding of the solar system will allow galactic tides and passing stars to strip away the loosely bound outer halo more efficiently, gradually eroding the classical Oort cloud and the most distant scattered disk objects until only the more tightly bound inner populations remain, populations whose orbits will have precessed and diffused under billions of years of perturbations, yet whose fundamental icy nature will persist in the cold darkness surrounding a cooling stellar remnant, a remnant whose feeble thermal radiation will provide the sole illumination for any surviving large TNOs, objects that by then may have collided, fragmented, or been captured into interstellar trajectories, their long isolation broken only by rare, close stellar encounters that could impart hyperbolic velocities sufficient to eject them from the Sun's sphere of influence entirely, encounters whose frequency increases as the Sun's motion through the galactic disk brings it near other systems over giga-year intervals, and this eventual dispersal underscores the transient character, even of the most enduring structures in the outer solar system, structures that appear immutable on human timescales yet are destined for slow dissolution in the broader galactic context, a context in which our Sun is but one among hundreds of billions of stars, each with its own retinue of planetesimals and distant icy debris whose chemical compositions and dynamical histories offer comparative laboratories for understanding the diversity of planet-forming environments across the Milky Way, environments probed indirectly through the study of debris disks around other stars via infrared excess, from warm dust and millimeter-wave imaging of cold belts analogous to our Kuiper Belt, disks whose architectures gapped, eccentric, or warped often betray the presence of unseen planets, shepherding material through resonances or scattering it outward, much as Neptune and the putative distant perturber may have shaped our own belt, and spectroscopic observations of these extrasolar debris disks occasionally reveal molecular emission lines from carbon monoxide or other volatiles released by collisions or sublimation, lines whose strengths and isotopic ratios provide glimpses into the volatile content of distant planetesimal populations. Populations that, like our TNOs, preserve pristine material from their natal protoplanetary disks whose properties vary with stellar mass, metallicity, and age, yielding a statistical ensemble against which our solar system's configuration can be measured for typicality or anomaly. And while our Kuiper Belt appears relatively depleted and dynamically excited compared to some young, massive debris disks, its survival to advanced age without complete collisional grinding or dynamical removal places it within the range of expected outcomes for Sun-like stars, outcomes that future large-scale surveys of trans-Neptunian-like populations around other stars may further constrain through microlensing detections of free-floating planetesimals or direct imaging of cold dust belts. With next-generation facilities such as the extremely large telescope or space-based infrared interferometers, facilities capable of resolving structures at tens to hundreds of AU around nearby stars, and thereby testing whether the processes that sculpted our outer solar system giant planet migration, planetesimal-driven instabilities, stochastic scattering, are universal features of late-stage disk evolution, or depend sensitively on particular dynamical histories that in our case included the rapid instability phase that reordered the giant planets and populated the scattered disk and Oort cloud, while leaving the cold classical belt as a relatively undisturbed relic, a relic whose binary-rich, low-inclination population continues to serve as a benchmark for quiescent formation conditions in the outer regions of protoplanetary disks, conditions likely replicated around many other stars, yet modified by variations in disk mass, viscosity, and external photoevaporation or stellar flybys, and returning once more to our own system. The synthesis of these broader perspectives reinforces the sense that the frozen worlds beyond Neptune occupy a uniquely privileged position as both endpoints of planetary accretion and gateways to interstellar space, gateways through which material and dynamical memory flow outward over cosmic time, carrying with them the chemical imprint of the Sun's birth environment and the dynamical scars of its early orbital rearrangements whose details remain encoded in the fine structure of orbital distributions, the patterns of surface colors and compositions, and the occasional preserved signatures of ancient collisions or internal activity that, though now dormant, may have once allowed localized melting and differentiation on the largest members, differentiation whose geochemical consequences could include the sequestration of heavier elements in cores and the concentration of volatiles in mantles, or transient subsurface oceans whose existence, if ever confirmed through future geophysical probes or more refined interior modeling, would expand the catalog of potentially habitable environments in the solar system beyond the traditional confines of Mars, Europa, Enceladus, and Titan, to include these remote, insulated reservoirs where liquid water might persist beneath kilometers of ice due to antifreeze solutes and residual radiogenic heat that diminishes only slowly over billions of years, and whose effects on surface geology remain discernible in the form of resurfaced terrains, fracture patterns, or cryovolcanic constructs long after activity has ceased. And as contemplation lingers on these possibilities, the narrative naturally circles back to the human endeavor that has brought such distant realms into focus, an endeavor marked by incremental advances in telescope aperture, detector sensitivity, orbital mechanics, and computational power, advances that have transformed faint moving points of light into richly detailed worlds of ice, organics, and orbital dance. Worlds whose study continues to humble and inspire by revealing the depth of interconnectedness between the familiar and the profoundly remote, reminding us that the solar system extends far beyond the orbit of Neptune into a twilight zone where physical processes unfold with the same elegance and inevitability as they do closer to home, yet on scales of distance, time, and energy that stretch the imagination that finds quiet fulfillment in the patient unraveling of these mysteries. One spectral line, one orbital integration, one new discovery at a time. Discoveries that collectively weave a tapestry of understanding whose threads reach from the icy surfaces of Pluto and Eris to the gaseous envelopes of protoplanetary disks around distant stars, threads that bind the local and the universal in a single, continuous story of formation, evolution, and quiet endurance in the cold vastness beyond. In the final quiet unfolding of this long meditation on the frozen worlds beyond Neptune, we arrive at a place where the accumulated details, spectral signatures etched in near-infrared light, orbital arcs traced across decades of astrometric precision, thermal fluxes measured in distant millijanskis, dynamical integrations spanning gigayears coalesce into something more than the sum of isolated facts, something akin to a sustained, almost musical awareness of the outer solar system's deep temporal coherence, a coherence in which every measured property of these distant bodies resonates with the conditions that prevailed when the gaseous disk still swirled around the infant sun, when planetesimals grew through gentle, pairwise collisions before the giant planets asserted their dominance and scattered the surviving remnants into the vast, cold reservoir we observe today. And it is precisely this resonance across time that lends these worlds their peculiar power to evoke wonder, for in their isolation and stillness, they preserve a record not merely of what happened, but of how slowly and inexorably physical law operates when stripped of the rapid, energetic cycles that define more familiar planetary environments. A record written in the gradual reddening of surfaces under cosmic ray flux, the seasonal yet century-spanning migration of frosts across low-gravity landscapes, the patient libration of arguments of perihelion within protective resonances, the faint residual heat leaking from decaying radionuclides deep within rocky cores, all proceeding at rates so measured that a human lifetime captures only the barest inflection of change. Yet change nonetheless accumulates, etching subtle distinctions between objects that share superficial similarities in size or orbit, distinctions that future generations of astronomers will refine with instruments whose angular resolution and sensitivity we can now only anticipate, instruments such as the proposed Large Ultraviolet Optical Infrared Surveyor or the Habitable Worlds Observatory, whose combined capabilities might at last allow resolved imaging of the largest trans-Neptunian surfaces, or the detection of tenuous atmospheric emission lines from bodies smaller than Pluto, or perhaps even the spectroscopic characterization of volatiles on Sedna-like objects during their rare perihelion passages centuries from now, passages that will offer fleeting windows into subsurface compositions, shielded for most of their orbits behind thick, inert ice shells, shells whose thickness and thermal conductivity continue to be modeled with increasing sophistication through multi-layer thermophysical codes that incorporate realistic regolith properties, porosity gradients, and volatile phase transitions, codes whose predictions are iteratively tested against the growing archive of occultation light curves, space-based photometry, and ground-based monitoring campaigns that track rotational light variations and color changes over years to decades. Variations that, though small in amplitude, encode the interplay between insolation, geometry, spin axis orientation, and subsurface heat transport. Transport that on some objects may still permit localized pockets of mobility, even as global equilibrium temperatures hover near 40 Kelvin or lower. Mobility that could manifest as slow creep of nitrogen glaciers, episodic outgassing of carbon monoxide through thermally activated cracks, or the gradual annealing of amorphous ice into its crystalline form under prolonged low-level heating whose cumulative effect over billions of years subtly alters the mechanical properties of the upper crust and influences the longevity of impact craters, whose morphologies remain among the most direct indicators of collisional history in this low-flux regime, a regime where cratering rates are orders of magnitude below those experienced by the inner planets or even the moons of the giant planets, rates so low that the largest classical Kuiper Belt objects display surfaces whose crater densities suggest ages approaching the solar system's own, surfaces that have accumulated only a handful of kilometer-scale impacts since the cessation of intense dynamical stirring. And this scarcity of craters, combined with the youthful appearance of certain terrains on Pluto and the inferred recent activity on other large bodies, points to a complex resurfacing chronology in which external impacts compete with internal and seasonal processes to reset or modify the visible record, a competition whose outcome varies dramatically with object mass, distance, and volatile inventory, yet whose overall effect has been to maintain a degree of geological freshness that belies the great age of the region, freshness that invites speculation about the possibility, however remote, of preserved prebiotic chemistry within subsurface environments, insulated against radiation and extreme cold, environments where liquid water-ammonia mixtures might once have existed briefly during early radiogenic or accretional heating phases, and where organic molecules delivered during formation could have undergone slow, low-temperature reactions over subsequent eons, reactions whose products might still await detection through future in situ measurements or extraordinarily sensitive remote spectroscopy capable of identifying complex macromolecular signatures beneath thin volatile mantles. And although such astrobiological potential remains highly speculative, given the prevailing temperatures and lack of sustained liquid phases, the mere presence of diverse carbon-bearing ices, irradiated organics, and possible subsurface volatiles ensures that these frozen worlds occupy a meaningful place in broader discussions of habitability across the solar system and beyond, discussions that increasingly recognize the outer solar system not as a barren periphery, but as a chemically rich archive whose contents may parallel those found in interstellar clouds or the disks around other young stars. Stars whose debris belts and distant planetesimal populations are now being characterized with sufficient detail to permit meaningful statistical comparisons that highlight both the uniqueness of our system's dynamical history, the rapid giant planet instability, the outward migration of Neptune, the sculpting of resonant and scattered populations, and the universality of certain formation outcomes, such as the prevalence of binary planetesimals in low-velocity environments, the radial sorting of compositions according to condensation temperatures, and the survival of primitive material far from the central star, material whose study continues to inform models of disk chemistry, transport, and dispersal, models that in turn feed back into interpretations of our own Kuiper Belt and scattered disk, creating a virtuous cycle of discovery in which local observations constrain global theories and extraterrestrial analogs illuminate processes at home, a cycle sustained by the patient accumulation of data across multiple wavelengths, multiple facilities, and multiple decades. Data whose quiet power lies in its capacity to transform the abstract notion of distant icy remnants into a vivid, interconnected landscape of worlds whose individual stories, Pluto's convecting nitrogen plains, Eris's seasonally collapsing atmosphere, Haumea's collisionally sculpted family, Sedna's extreme isolation together, compose a single, extended narrative of solar system evolution that stretches from the hot, dense phases of disk accretion through dynamical clearing and outward scattering to the present twilight state of slow, almost imperceptible change that will continue long after human observation has ceased, carrying these frozen sentinels forward into futures shaped by the sun's eventual expansion, the galaxy's relentless tides, and the occasional gravitational handshake with passing stars, futures in which they may persist as dark, refractory cores, orbiting a dim white dwarf, or drift into interstellar space as solitary wanderers, bearing the chemical memory of a long-vanished planetary system, a memory encoded in their ices, their organics, their silent orbits that once danced in resonance with Neptune, and now trace paths through the wider Milky Way, paths whose ultimate trajectories remain unknowable, yet follow the same immutable laws that have governed their journey from the beginning, laws that bind the smallest planetesimal to the largest galaxy, in an unbroken chain of cause and consequence, a chain whose contemplation in the stillness of these distant frozen worlds brings a profound sense of continuity, of belonging to a cosmos whose history is written not only in violent births and cataclysmic collisions, but also in the patient, meditative endurance of cold and silence. Endurance that these trans-Neptunian bodies embody with an elegance that transcends their physical modesty, an elegance that lingers long after the final datum has been recorded and the last model run to completion, leaving behind a quiet invitation to return again and again to the frontier beyond Neptune, there to listen once more to the slow, measured breathing of a realm where time itself seems to pause and reflect upon its own vastness.